Welcome back, AP Stat. This is Chapter 18, Part 2. We're going to get into how confidence intervals are made. Last time, we talked about what confidence intervals are and what they do. Now we're going to be talking about how precisely we make a confidence interval, really the anatomy of a confidence interval. So we need to talk about margin of error. All confidence intervals can be written in the form estimate, that is point estimate, plus or minus ME, that is margin of error. Going back to a prior example, the 95% confidence interval for the true proportion of those diseased sea fans in that one reef off the coast of Mexico is 0.519. That's my point estimate, my one number guess at the true population proportion of diseased sea fans, plus or minus 2 times 0.049. And that 2 times 0.049 says, well, the 0.049 says that is my standard error. And the 2 means I want to go 2 standard errors to the left and right. That's what the plus and minus is for. To the left and right of my point estimate. So I am 95% certain that I am going to catch, as it were, the true population proportion of diseased sea fans in that interval. So let's look at a little recap and then a question, okay? The Pew Research poll asking how often do you read any newspapers in print reported a margin of error of 1.5%. It is a convention among pollsters to use a 95% confidence level and to report the worst case margin of error based on P equals 0.5, right? So why would P equals 0.5 be a worst case margin of error? Well, if we look at the formula for standard error or standard deviation for a sampling distribution of sample proportions, you'll notice it's square root of P times Q all over N. So if we make P and Q both 0.5, if P is 0.5 and Q is 0.5, then we maximize our standard deviation or standard error, okay? Makes that square-rooted fraction as big as possible. So that's a worst-case margin of error, okay? One thing that this problem does not explicitly mention in the book, but what we'll need to recall is that N is equal to 4654. That is the sample size. And if that looks like a really big sample size to you, when dealing with proportions, we need really big sample sizes to get good confidence intervals. And that is something you'll find to be true as we go through this section. Question: how did the researchers calculate their margin of error? Okay, so here is how they did it. The standard deviation of the sampling distribution for sample proportions is a square root of PQ over N, as I have said. Okay, so we can use standard deviation since we are assuming that P is equal to 0.5, worst case scenario. Square root this expression right here, and we would get 0.0073. So for the 95% confidence interval, the margin of error is 2 standard deviations, in this case, to the left and right of my sample proportion, point estimate, times the size of the standard deviation, which we just calculated, is equal to 0.0146. The margin of error is just a bit under 1.5%. So we need to compute a standard deviation and then multiply that by the number of standard deviations to the left and right of my point estimate, and that is the margin of error. So we've seen there are 2 parts of a margin of error. There's the 2 that we keep seeing for 2 standard deviations or standard errors away from the point estimate. And there is the standard error or standard deviation. Now, does that 2 or any other number we could put in place of the 2, does that have a name? It does. The name is the critical value. So to change the level of confidence, we need to widen or narrow our net by adjusting the number of standard errors, or in the prior example, standard deviations, we consider to the left and right of p hat, our sample proportion. The number of standard errors to the left and right of the sample proportion we would consider is called the critical value. For example, in our confidence interval, which you have seen a couple times now, the 2 is the critical value. Now, I use 2 in quotes because technically the critical value that would get me 95% confidence is 1.96, which, it rounds to 2. But technically it is approximately 1.96 standard deviations or standard errors. And that would give us the confidence level of 95%. But we use 2 as an approximation. Why? Because you already know the 68, 95, 99.7 rule. So you're used to seeing 2 standard deviations to the left and right of the middle of the bell curve encapsulates 95% of the area. That's why we use the 2 here. But technically, going forward, we're going to be seeing the number 1.96 instead of 2. A critical value, specifically for the normal distribution, the normal model that we've been using, is denoted Z, but that's a little confusing because you usually associate Z with standard score. So sometimes people use Z sub alpha, but again, that's not what our book uses. Z star is what our textbook uses. This little symbol right here is called star. So Z star is what our textbook uses, and personally, that is my favorite notation, so we'll go with that. What a critical hit. Here are some common critical values for 90% confidence for the examples we've been referring to involving the normal model. Z star is equal to about 1.645, all right? 1.645. For 95% confidence, Z star is equal to 1.96. Again, 95% confidence, 95% of the area under the bell curve is about 2 standard deviations to the left and right of the mean. You've known that since the very beginning of the year. 99% confidence, Z star is equal to 2.58. That's pretty far out on the bell curve, but if you want to be 99% confident, you need a really wide confidence interval. Any other confidence level, we would use inverse norm, mean centered at 0, standard deviation of 1. That setting allows us to count standard deviations relative to a mean of 0, and that's great for computing critical values. So, find the critical value Z star for a confidence level of 96%. To do this, we're going to sketch a normal model to aid in the calculation. Here's a normal model I could use. 96% of the area is shaded. That gives us 96% confidence. The question is, what cutoffs over here in the blue would give us 96% confidence? Those cutoffs are going to inform us about the critical value, all right? And specifically this positive cutoff here, because remember, a critical value is how far we go to the left and to the right. So a positive critical value to the right, positive critical value to the left, we're going to be looking for this cutoff right here. So let's go to the calculator now. So here we are at the calculator once again. I'm going to go to second distribution and go down to inverse norm at number 3, or just click the number 3. Now, this is an older interface than some of you may be using. If you're using a TI-84 plus CE, you'll have the left, right, and center option. All you'll need to do is enter 96%, mean of 0, standard deviation of 1, and then click center. But if you have an older calculator, you need to think a little more about this. I'm actually going to enter 0.98 because I want the right cutoff for 96% in the middle. And if 96% in the middle, then a total of 4% is going to be at the extremities, 2% on either tail. So I want to include the 2% left over on the left tail plus the 96% in the middle. That would leave 2% on the right tail. 98% is the area that I want to work with, because in old calculators like this, we start, the phrase I often use is chomping the area. We chomp the area from the far left-hand side of the bell curve and proceed to the right. So I would want to chomp an area of 98% to get that left tail and the 96% in the middle. Mean and standard deviation are already at 0 and 1. It's like the calculator read my mind. It's an automatic setting. All right, so we hit enter, and bada bing, bada boom, about 2.05. So the bell curve didn't lie. I used a little applet online to create that bell curve from University of Iowa. Shout out to University of Iowa. And I got the bell curve said a little past 2 standard deviations to the left and right of my sample proportion. And that is exactly what the calculator is saying. Good job, calculator. Good job, University of Iowa. So now let's talk about what happens when we change our critical value. Let's go back to a familiar problem. In the poll on reading newspapers in print, Pew Research found 52% of adults reported hardly ever or never. They reported a 95% confidence interval with a margin of error, if you recall, of 1.5%, 0.015 approximately. Using the critical value of Z and the standard error based on the observed proportion, all right, so we're computing a standard error this time, what would be the margin of error for a 90% confidence interval? And what is good and bad about this change? So let's see what happens when we change our critical value to adjust for a 90% confidence interval as opposed to a 95% confidence interval. So let's lay down the details here. Our sample size is 4,654, if you recall from the prior problem. No shame if you didn't remember that. P hat, our sample proportion, is 52%. So the standard error, not standard deviation, we're using some sample data for an approximation, for P hat is approximately equal to the square root of P hat Q hat over N. P hat is 52%, Q hat is 48%, N is 4,654. Throw that in a calculator and you get that little tiny number right there, just north of 0.7%. So, for a 90% confidence level, Z star is equal to 1.645, right? You'll remember some of those Z stars from one of the prior slides. So the margin of error would be Z star number of standard errors times the size of the standard error, which is going to be approximately 1.2%. So what's good and what's bad about that? Now the margin of error is only about 1.2%, and that produces a narrower interval, our textbook says. What's good about the change is that we now have a smaller interval, okay? Smaller interval, more precise estimate. However, what's bad is that we are less certain that the interval actually contains the true proportion of adults who never or hardly ever read the newspaper. Our level of confidence goes down from 95% to 90%, so we're a little less likely, by the tune of 5%, to get the true population proportion in our interval. However, our interval's a little smaller, it's a more precise guess. That's the catch-22, if you've ever read the book or heard of the book or understand the concept of a catch-22. That's the catch-22 here. The wider you make your interval, the more likely you are to catch the true population proportion, but an interval too wide is kind of useless. It's not a very accurate, or I shouldn't say accurate, it's not a very precise guess. But if you make your interval too small, then you're less likely to catch the true population proportion. A catch-22 is either way, there's something to be gained and something to be lost. All right? And that's what's going on with confidence intervals. Now we're going to look at confidence level and margin of error in a couple of examples. Think some more about the 95% confidence interval originally created for the proportion of US adults who never or hardly ever read the newspaper in print. Consider these three statements here, three questions, and figure out what you would say in response. Pause the video, try each of them, and unpause the video when you want to go over the answers. Okay, I'll assume we're ready to continue. Let's look at number 6. If the researchers wanted to be 98% confident, would their confidence interval need to be wider or narrower? Well, the answer is it needs to be wider. The higher the level of confidence, the greater the margin of error. Think about it. In order to increase your level of confidence, you need to increase Z star, which makes for a wider margin of error. Let's look at number 7. The study's margin of error was about 1.5%. That's our original example. If the researchers wanted to reduce it to 1%, would their level of confidence be higher or lower? So the margin of error is decreasing. What's going to need to happen? The answer is lower. Smaller margin of error means lower level of confidence. If you make your margin of error smaller, you're making your net to catch the true population proportion smaller, which means you're less confident that you're going to catch that population proportion. Number 8, and this is the most important question by far. If the researchers had polled more people, would the interval's margin of error have been larger or smaller? And interestingly, smaller is the answer. The margin of error would have been smaller, mind you, without reducing the level of confidence. And that's important. Note that the margin of error is z-score times the square root of PQ over n. So as n increases, since n is in the denominator, even though it's in a square root, doesn't matter, n is in a denominator, the margin of error is going to decrease. If you increase a denominator, regardless of whether it's in a square root or not, you are decreasing a value on the whole. So the margin of error decreases without decreasing the level of confidence. This is important, and the importance we'll see next time.